Okay, now we are ready to attempt the first question. And the first question is probably very interesting for my students, okay? Because the first question is related with a three-phase fault, okay? Probably you are wondering, okay, this is a class about asymmetrical faults. Why do we need to attempt the three-phase short circuit calculation? Okay, all of you are right. Three-phase short circuit is basically a symmetrical fault. You can use the Thevenin method, and it's extremely simple to calculate the short circuit currents. However, here I am doing something quite interesting for my students, and it's what I want to do is show my students that you can use symmetrical components even if you are not if you are not in an asymmetrical condition. Okay, let me tell you the following. Let's start the explanation, and I will show you what is the point of this exercise. Okay, let's assume that we have a three-phase power system like this, and we have the terminal. This is the point F, and we have here A, B, C. What is the typical configuration for a volted or solid three-phase fault? Okay, when we use the term volted or also solid, we refer that the impedance fault is equal to 0. Okay, let's assume that we are working with a solid or a volted three-phase short circuit, and in this case the three-phase short circuit, as you can see, we are connecting A, B, C together, and we are going directly to the reference. And what are the terminal conditions? Okay, if we take the terminal A, B, and C, and we connect together, and going to ground, the terminal condition is extremely simple because there is no fault impedance. The voltage is the same voltage as reference. And to be honest, this is a very serious condition. The three-phase short circuit is a very serious condition because we are imposing zero voltage to the three phases, the three lines A, B, and C, okay? And what we need to do now is, you must remember, in order to get A, B, and C 0, that is equivalent to the positive and negative sequence and zero sequence, all of them equal to 0. Now, what we need to do is use this identity, this condition, this terminal condition at the positive, negative, and 0 sequence, and see what is the symmetrical currents moving inside the circuit. Okay, if you look over here, 0, positive, and 0, negative sequence, the three are 0. This is also 0. Okay, and in this case, we are closing loops. But in zero sequence, they are not voltage sources, and as consequence, the zero sequence current is equal to 0. In the negative sequence, again, they are not voltage sources, and as consequence, the current is 0. And the only place that we have active components and we have this voltage source is at positive sequence. To be honest, it's very simple for my students. This is circuit analysis. And from circuit analysis, we can see that the positive sequence current is the division between the voltage, the pre-fault voltage, divided by the total impedance in this circuit, and that is the positive sequence Thevenin. Well, if we put the number together, we obtain what we were talking about: zero sequence, negative sequence, both of them they are 0, and there is only positive sequence. Okay, as you can see, the angle of this positive sequence current is minus 19, minus 90 because it's minus 90 because it's coming from this J that is inside the denominator here at the Thevenin impedance, okay? Well, what I will do now is my main objective today. What is my main objective? Well, we are talking about symmetrical components, and I would like to show you that even if we are working inside a symmetrical fault, and this is the case of the three-phase short circuit, remember symmetrical three-phase short circuit is a symmetrical fault, but we can use symmetrical components to calculate the currents, okay? If you must remember from my classes, there is a relationship between the symmetrical components and the asymmetrical components. What I'm telling you, this is a positive, negative, and zero sequence, and this is ABC. And to move from zero, positive, and negative to ABC, we use this matrix over here, the matrix A, and that is the transformation matrix, okay? A is this very interesting and very important matrix. And this small letter A, you must remember that that is an operator, and that is 1 at 120 degree, okay? That is a complex number. Well, but if we take those currents here and we put inside, remember this is 0, they are only positive sequence component, and we use the calculator or we use MATLAB, whatever you want to use. Wow, here we obtain what I was looking for. As you can see, when I use the symmetrical components inside this matrix, I can obtain A, B, and C. And the most beautiful part here, look the polar representation. If you look the polar representation, there is a current here at minus 19, there is a current here at 30, and there is one current here going to 150. This is the current A, this is the current B, and this is the current C. That is the location, the phasor diagram for the three-phase per unit current. And you can see that there is 120 degree here, there is 120 degree here, and the magnitude of those currents, they are the same. What I'm telling you is that the magnitude A is equal to B, and that is equal to C, and that is equal to 2.89 per unit. What I'm telling you is that we use symmetrical component to calculate a three-phase short circuit. And we are demonstrating that this is a three-phase short circuit because A, B, and C, all of them, they have the same current, okay? Well, but these currents over here, A, B, and C, the short circuit currents, they are in per unit. And in this problem, I was asked about the amps, the real current, because amps per unit is very useful, very important when you are calculating in power system. However, for real life, the amps, they are the most important unit, because if you are using overcurrent protection or you are designing circuit breakers or you are specifying bus bars, you need to use amps, okay? Well, to obtain the real current in amps, what we need to do is multiply the per unit current multiplied by the base. And we know the base because we calculate before at 66 kV, the current base is 874 amps. We combine here in this equation and voila, we obtain here the three currents. And the most interesting thing here, as you can see, we have 2.35 kiloamps in each line. This is a three-phase fault. This is a three-phase fault, and it's very simple for my students to see that the magnitude of the three currents, they are the same, 2.35 kiloamps, because this is a line to line to line three-phase short circuit.